Okay. Silence can either mean it's going really well or really bad. Any comments about week 6? How are you finding it? How are the things that you learned? Or have you gone through the videos? How are you finding it? Anything related to the course? Okay, Sanjay is saying not started week 6. Others also, is it the same?
Yes, sir. Actually, we are on the week 5
So
only.
not able to hear you.
Uh, can others hear me?
Yes, sir.
Yes, sir.
Not quite audible.
Probably
Okay,
the problem is on his end.
okay, Shamit.
Yeah. Now I can hear you. Okay.
Okay. Yeah. So I guess most of you are still on week 5. Is that the case?
Yes, sir.
Yes, sir.
Yes, sir.
Okay,
Yes,
I
sir.
guess it's because of the quiz, right? You all were focusing on the quiz.
Right.
Okay, how did
Yes,
the
sir.
quiz go? How did the quiz go?
Okay.
Quiz went well, but I would say that the multi-select questions, I just messed up with the options.
Okay. Okay. So I guess your deadline for graded assignments is four, third or fourth. When is it? I
Six.
forgot the date.
6th
6.
Feb.
6.
Six. Sixth. Okay. Good. So we have time. So if you have understood week 5, week 6 is broadly speaking, it is uh, 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 yeah. So week 5, you were introduced to the different graph algorithms, right? Like the Dijkstra's, Bellman-Ford, the spanning trees. So, and the the complexity of many of these, I think most of them is n square, right? And in week 6, what will be the main thing which we'll be looking at is some data structures which will help you reduce the complexity to something less than n square. Okay, more specifically, it is m plus n log n for Dijkstra's and Prince. Yeah. So you'll be going through some data structures which will which you will apply back to uh, these algorithms. So yeah, so I think if you're good with week 5, week 6 is mainly about these data structures. So I think you will hopefully week 6 should not be that difficult. But yeah, understanding those data structures might take time. So yeah, that's it. So okay, so then let's jump into the doubts. What do you all want to discuss today? Any specific thing anyone has in mind? Yeah, you can go ahead.
So this Belmont Ford, this negative cycle and negative age, this thing I need a little bit discussion, sir. It's not able to.
Bellman Ford, uh, negative. Okay, so is your question if there is a negative cycle
Hmm.
in Bellman Ford, right?
Right, sir. First of all, I don't understand how the age can have a negative one, means negative weightage. In which circumstances I can consider this to be a negative one?
Okay, that's a good question. When can an edge have negative weight? All right. Okay, Shamit, yeah, those are good questions. I'm just, what I'll do is I'll take all the questions at the start, and then we'll see which to take, and let's see if there are uh, related questions, and then we can take all of those together. Yeah, others, okay, so
And
Shamit was talking. Yeah,
and
yeah,
I
Shamit.
also do have a question in minimum spanning tree.
Hmm. Any specific question?
Question means what sir told ki you can develop the minimum spanning tree in two way. One by means removing the edge and you can come with the minimum spanning tree, and another one you can grow from the small one to this part. How can I grow that thing? This is not very clear to me.
Hmm. Okay. So basically, the explanation of both the algorithms, right? Prims and
Especially crucials, right?
Kruskal's. And sir, all this algorithm where we are forming this tree,
hmm.
do we use the linked list anywhere in this while we are coding this thing? Where is the use of linked list over here? Is there anything?
Uh, so in the I think in the explanations which Sir gave, Sir is using an adjacency list to represent the graph,
Hmm,
right?
hmm.
So well, you can think of the adjacency list as a linked list, right? In a way.
Yeah, but whenever I saw any program means which is using this kind of data structure to solve any problem, they are
Hmm.
nowhere they are using this linked list concept. Means I'm means if it is not used anywhere, then I don't know where we are actually using in practical part the linked list one.
You're talking about the left, right, all of those things, no?
Yeah.
Okay, okay, got it, got it. So was that for a tree, right? Sir explained that for a tree, right?
Yes. Yes.
So this is actually week 6. This is a separate thing, I think, right?
Okay. 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 Okay.
No, no, I'll. You are referring to week 6, right?
A part of week 6 anyway. Okay, that you can take later on, no issue.
Binary
No,
search
no.
tree, I guess.
Right.
Yeah. So your question is why linked list, right?
Yes, sir.
Okay. All right. Okay. All right. What about others? Any other difficulties, any doubts, any concerns?
So the worst case of Bellman fold algorithm.
Worst case of, okay. Okay. Worst case complexity, you mean?
Yes, sir.
Okay. All right. Okay. Any questions about heaps, binary search trees? I know all of that is week 6, but anything related to that? All right. So I think Bellman Ford algorithm, many of you have some doubts. Then minimum spanning tree. Okay. Uh, Specifically, the doubt is how do these algorithms work, right? I think that is one doubt which you all have. And why are we using a linked list for a tree? right? Okay, so let's start off. Okay, so what I've done is, okay, so let's look at the Bellman-Ford algorithm. So before that, are all of you have all of you understood Dijkstra's algorithm? Any doubt in Dijkstra's? Okay, so now I want you all to type into the chat what what is the purpose of the Bellman-Ford algorithm? What does it do? What does Bellman-Ford do? Okay, just got one answer till now. Okay, only Viraj has answered. Others, yeah. Okay, right. So,
Sir,
yeah.
I have one more question. Can you explain once again, like why cannot you use the negative edges in the Excel algorithm?
Okay, sure. Yeah. So why won't Dijkstra's work with the negative weights? Okay, right. So Dijkstra's and Bellman-Ford both are used to calculate the shortest path from a given source, right? We have a source vertex and we want to find the shortest path from that start vertex to all the other nodes in the graph, right? And Dijkstra's can be used if there are no negative cycles, but sorry, there are no negative weights. But Bellman-Ford is an improvement on that, where there are if there are negative weights, you can use Bellman-Ford. So Shamit had a question on when can an edge have negative weight? What is the meaning of that? Others, anyone, do you want to respond? Like, can an edge have negative weight, and any real life example or something which is coming into your mind? Nothing? I, okay. Yeah, so I think Shyam is telling about, sir gave an example of a cab driver returning home, right? So let's say you're a cab driver, you are returning home. So on the way, let's say you have to uh, pick up some people, and because of that, and if it's towards your home, then in a way it is good, right? But if it's further away, then the cost becomes positive or something like that. So in short, if there are multiple things going on, right? Multiple criteria, right? And some criteria might hinder the distance or hinder your progress. Others might help you. So in that way, if you see negative weights are possible, right? So in a way, you're reaching. Uh, so don't think of it as a physical distance, right? Of course, physical distance from point A to point B cannot be negative, but think of it as some constraint, and maybe from a point A to point B, if you have to reach, then in a way you can reach faster compared to other ways. That is one way to think of it. Shamit, did that answer your question in some way?
Uh, if you can means give some more means. I'm still not get the clarity of the negative age. I'm not able to relate that thing with some practical thing where I can understood clearly कि oh, this thing is happening. The
Okay.
process is okay, it is just a mechanical process, but I just try to relate with the practical thing.
Okay. Let's see what Bellman Ford is doing. All right. So let's see if I can try to explain from this, right? Mm, yeah. In a way, what it's telling is so for example, if you're going from 5 to 2, uh, what it's saying is that, uh, you let's say you take some n resources to go from 5, so from one place to the other, for example. Yeah, so consider maybe
Sir, in a like cost and incentive kind of paradigm, if a cost is there, then we can take it
yeah,
as positive. If there is any incentive, then we can take it as a negative. So that can also work
maybe,
out.
yeah, that is one way, right? So let's say I want to reach from 5, I want to reach 2. This we are thinking of distance, right? But if we consider, let's say, the time required, if time is the metric, maybe you can reach from 5 to 2 using a public transport or a train or something, versus if you had to walk from 5 to 2, right? So, uh,
Actually, sir, both time and cost, the negative is does not means relate or sense in that way because we never say ki minus 4 rupees or minus 3 second.
yeah, but someone was mentioning this incentive at cost, right? Who can you elaborate on that?
Yeah, you can take any unit and just think in reverse way. I do not have any problem on that. Actually, I try to think what is that practical situation when I can means when I'm constructing this graph, I can generate this plus and minus. I just want to know the practical use. Then it will be clear to me. Oh, this is happening actually.
Yeah. Even I'm just trying to think of a good example. Mm, yeah, this is not a very good example, but so let's say uh, this is the uh, let's say these are uh, yeah, the edges refer to money which is required to travel from 1 to 5 or something like that, for example. So 1 to 5 you require 2 rupees to travel, but there is some special scheme wherein if you want to go to 2, the the government or the bus will pay you 2 rupees, okay, to reach there. So if I want to reach from 1 to 2, for example, let's say this edge was, it's going from 1 to 2. So you can either take some transport which will cost you 1 rupee. Assume this arrow is going from 1 to 2. But there is another way you can go from 1 to 2, wherein if you go from 5, you can spend 2 rupees. You have to spend 2 rupees initially. But once you reach 5, there is a service which will take you to 2 and which will pay you 2 rupees back.
Okay.
Sir,
So
It is
maybe
some sort of that cab driver example means while returning the home, I supposed to burn my fuel, but instead of that, if I take some people and I'm collecting the money, that is why it is negative. In that way,
exactly.
we
Yeah,
can
yeah,
correlate.
yeah.
Okay.
Yeah, someone else was talking.
No, sir, I'm talking about the same, the cab example.
Yeah. Yeah. So that's possible, right? So yeah, so okay, so let's look at Bellman Ford. Yeah, let's try to see what's going on here. So Bellman Ford, what you're doing initially is you are finding out the rows and columns, right? And then you are uh, calculating the maximum distance and storing it in infinity. That is the value. And initially you set all the distances. So you have a dictionary called distance, which will set everything to infinity, right? So let me take this as,
Hello, sir.
yeah.
So how can you find the maximum weighted edge?
Sorry.
In infinity, or finding the maximum weighted edge, right? So
Yeah. So this is the NumPy function, which will take the entire matrix and it will find the maximum in that.
okay, sir. Without using that function, we can't find that.
Yeah. Without that, you can't.
We can find that, but we have to implement a list of plates, nested list, and then apply for loop.
Yeah. So in a way, the complexity is the same, right? Or will it be different?
Yes, sir. Complexity is same because the size of the matrix will be same in both cases.
Yeah. All right.
Sir,
Uh,
sir, a shape function will give a value of row and column, but it will also give the value of x. I understand that is the weight. Is it the case?
Sorry, I didn't get you.
Sir,
Majalik, yeah.
yes, sir, I'm telling that a shape function will give the shape of matrix, but here one value that is x, that is the weight. That shape function will give the value also that is stored as a weight in a matrix.
Oh, got it. Yeah. So actually, the shape of this matrix. So this is actually what do you say? It's a three-dimensional matrix, which the first one is row, the next one is column, and the third one is the edge, the weight of the edge. So this is like the weight of the edge. So the shape, so when you out the output of wmat.shape in this case will give you three values: the row, column, and the weight.
Sir, it will be total weight.
Sorry,
It will be total weight. I mean, the x, value of x.
total weight as in?
Sir, means what is x? Rows is okay. Rows is number of rows, number of columns. I got it. But what is x if
X
in
is
this case?
the value, means in the I and jth column, if there is a edge, then what is the weight of that edge? If you can think this matrix x and y in two dimension, and all the weight is the corresponding height of that particular ijth field, if there is edge, in this fashion you can think. So it is look like a means city. In your city there is a some tall building inside many grid. The grid which is having the building, it is the edge of that matrix, and the height of this building, it is the weight of that particular ith jth weight of the matrix. You can
So
think in this way.
for the current matrix, what will be the value of x in that case?
uh, for the current matrix, for each, it will vary with the row column value, na? Say,
Oh,
I'm
I
not
got your
getting.
question. So your question is, for example, row. So in this case, sorry. So in this case, rows is actually, what is the data type of rows?
Data type it should be numeric, right?
Integer.
Integer, yes.
Okay. And what is its value?
Eight.
Okay, let me just take you through
Actually, for
what's
this
our
graph, it's 8 by 8 matrix, right? 8 nodes are there, so rows would be 8 and columns would also be 8.
right? And what will be the value of x then?
Yeah, that's what I also didn't get.
X will be 1
Yeah,
and
wait, I'll just show it. Where is that? Yeah. So no, I think it's there. Yeah. Okay, I remember somewhere was defined.
And also in Google Colab, actually, wmat.shape, it doesn't work for me because I always have to do np.shape, and then in bracket, if I give the matrix name, then only it returns rows and column.
So see, if you consider this graph, right, you have the rows, columns, right, and uh, each of them, yeah. So and you have a 0 and a 1 associated with it, right? So yeah, so this is a list, and if you yeah, so this will actually be a n cross n cross n matrix, right?
Yes, sir. That's what I said. N-dimensional matrix. It will represent n-dimensional matrix, and the value of n will like x will be from 0 to n minus 1.
Then it depends on the weights, right?
no, last one can't be n. Na,
It will be 2
x
only.
can maybe any value. We cannot
So,
restrict x to n.
sorry,
Yeah,
what
I am not restricting. I am saying that it can be.
Yeah, it can be, but it may not be.
Yeah, you are right. We can form as many matrices as we want to. Like we are defining the dimension of the matrix, right?
Yes,
You can see this in Floyd Warshall algorithm. Sir has used this x value there
in
for defining.
yeah, Floyd Warshall, right?
Yeah, sir.
So, yeah, so in this case, the shape is, yeah, because there are we are moving across k plus 1, right? That's why. Okay, so the question is, what is the value of x, right?
X is people, which represent if there is age present, it will be 0, 0, and if age present, it will be 1 and the age weight. And if there is no age present, it will be 0, 0. So actually, this x is size of that tuple. If we had three components, like then it would have been 3. X would have been 3.
Right. So in this case, when we saw this, right? So you're saying in this case it will be 2, right? Because we have two components.
I checked it on the IPI, the collab notebook provided by sir. It is giving me answer 2. So I inferred that it must be the size of the tuple.
Okay. Yeah, I have to check that. Okay. Yeah, sorry about that. So this is actually, instead of weight, it is the size of the tuple, right? Okay. All right. So then initially we initialize all of the distances, so 0, 1, 2, 3, 4, 5, 6, 7, all of them to infinity, right? And what we actually do, let's initialize all of this to infinity at the start, and then we start from the source, which is S, and that becomes 0, right? And what we actually do now is we run it for, yeah, so we take I for the range in the rows, right? So at each step, like in the first step, we calculate all the distances from 0 to, you know, yeah, so the distances between 0 to one vertex. Okay, so what is the distance between 0 to 1, 0 to 2, 0 to 3, 0 to 4, 0 to 5, 0 to 6, 0 to 7, right? So we look at the edge weight. So in this case, let's take U as 0, V as 0, right? And we check if U, V, and 0, which is if there is an edge, right? So in this case, there's no edge. 0 to 1. Now, the next time if you see, it will be 1. So 0 to 1, there is an edge, right? And remember, 1 initially is infinity. So then you look at the minimum of the distance between distance of V, which is 1, which is infinity, and distance of U. So from here, in this case, this is U, this is V. So the distance from U to whatever is the weight from U to V, right? So it's actually the distance between, yeah, so the minimum of the distance, in this case, it is infinity, and distance of U we know is 0, right? 0 plus 10, so this becomes 10. Then we iterate over the columns, and then so we for an edge we in the first time we look at its immediate neighbors, right? And whichever if there is a direct edge, we update the distances of that. So in this case, this will become 8, right? So now what happens after that, right? now in the second iteration, what will happen is, again we iterate from 0. Yeah. So then again we do the same process, right? But now since the distances are updated, we will be getting different values, right? So let's try this. So let's take u as 0, v also as the 0, let it be. So let's take v as 1, for example. Now we look at the minimum of distance of v. In this case, this is v. Uh, yeah, so here we see that there isn't much, there isn't a difference, right? Minimum of distance v is 10 and distance of u plus distance of u is 0 plus 10, so it's the same. So no change. So we do this, right? So in this case, this becomes, then we check for 2. We check for 2. There is 2. 2, there isn't a path from 0 to 2, so we neglect that. 3, 4, 5. Okay. Now what happens when we reach 6? Okay. So in this case, u is 0, v is 6. So what happens is we look at minimum of distance of v. Distance of 6 is infinity, right? But what is distance of u? 0 plus w mat uv. Okay, so v is 6. Oops, sorry. Okay, so distance of v is 8 and minimum of distance of u. U is 0 plus u comma v. Sorry, there is distance of u is what? Distance of u is 0. Oh, sorry, I made a mistake. U in this case should be 7, right? So what we see is that distance of u, 7, is 8, and w mat u of uv, which is 7 to 6, that is 1, right? So distance of v, in this case, instead of infinity, so initially we could not reach 6, but now we can reach 6 through 2 steps. And how did we reach that? Because in the previous step we could reach 7, and now in this step we can reach 6, right? So that's why now this gets updated to minimum distance of v initially was infinity. Now this gets updated to 8 plus 8, which is distance of u, plus 1, which is 9. So this gets updated to 9. Was this clear? Any doubts?
Sir, why we are taking 2 times the range of rows? For I in range rows and for u in range rows 2
Yeah.
times.
So if you notice, we are not using I anywhere, right? We are not using I anywhere in the code. Okay. So what we are doing is we are repeating this process n times, or the number of nodes which are there in the graph. We are repeating it n times. So the first time, so what's happening is, yeah. So the first time, what will it do? It will look at nodes which can be reached from one hop. Okay, that is when I is 0. Okay, it is checking for this. Okay, when I becomes 1, as in the second time, again this whole thing is repeated, right? But now we know we can reach 7 and 1. So in the next when in the next value for I, we will look at the next hops where we can reach. Then when I becomes 2, we again look at the next hops which we can reach, right? And we go on till we reach till we so in each step we are doing one hop from the main source, and we'll continue that till when? Till the last node of the vertex. Sorry, last node of the graph. That's why we are again doing this n times. So
So,
this very well might, yeah.
so basically we are checking from a source destination source to how many hops we can reach to each vertex. Then we repeat for all vertexes, making them as a source.
Sorry.
Firstly, we looking from 0, where can we reach in one hop, and then 2 hop, and then 3 hop, and then we are repeating for other vertices for same process.
No, we are not repeating for other vertex. We are repeating only for 0. I mean, whichever is the start vertex, right?
Okay.
As Professor said that Bellman 4 stabilizes after n-1 updates. So that's why we are using this outer loop.
Okay.
Any doubt in this algorithm? Like, did you all get an intuitive sense of what is happening? So the first time this runs, right? We do this for uh, all the vertices, right? And the second time it's run, we do it for, we calculate up to two paths. I mean, paths which have two vertices from the source, then 3, then 4, then finally n minus. We do this n minus 1 times. So in n minus 1 times, what are we getting? We are getting paths of length n minus 1 from 0. And what does that mean? That gives me paths from 0 to all the other vertices. So that is what is the single source shortest path. So I had, yeah, any doubts in this? Okay, so now So the question I think which Shamit had was, why doesn't this work for paths with negative cycles, right? Shamit, that was your question?
No, that part is clear. Actually, that is there. Means that I know, sir. Why it is not working for the negative cycle.
Okay. because then it won't stabilize, right? Because
Right, right.
each time you run this, so for example, the n minus 1th time, so this minimum, because of this minimum, the n minus 1th time you run, for example, this will be some value, it will be -2, -2, -4, +1, -3. Okay. Then whatever is your value, the next time it will be lesser than this, right? It will be -3, -3, which will be -6. And this will never converge, right? Because of the minimum thing. That's why it won't work for negative cycles. Okay, any doubt regarding this?
So in general, sir, when do we close or can say the Belmont-Ford this algorithm is over? Uh, we have to run this nth time, right? Because in n minus 1 it gets stabilized, and if I run one more cycle, I get confirmed ki yes, it is stabilized. Then only I can stop.
Yes, yes. Yeah.
Then why should I write for I in range of rho plus 1? Because it is now stopped at n minus 1th time. I'm not checking ki whether it is stabilized or not. Because if
Yeah,
I
yes.
uh,
Yeah, go ahead.
no, that is my question, sir. Because I am stopping here at n minus 1 time. I know ki in n minus 1 time it gets stabilized. To double check, shall I go one more iteration to confirm yes, it is stabilized?
Well, you can, but no, but one thing, I in range rows is running from 0 to n minus 1,
Right.
is n times, right?
Yeah, but if you sir open the means that search lecture, that one table,
Ah, right, right, right.
then it is easy, sir.
I think is it this one?
No, go ahead, go forward, sir.
No, this is no 5.1, 5.2. Is it 5.3? Yeah. Yeah, I got your point. So why aren't we checking
No,
for
you go to the you go to the table, sir. I just have one question. Yes, this one. You go, yeah. Wait. Now, now from this point, apart from node number 4, everything gets stabilized. I can see that. See, every numbers is repeating, but the node 4, it's not repeating. I don't know. If I run one more step, then it's probably this is 0 5 5 6 9 7 9 8. Then I can say ki okay, it also stabilized for the node 4.
Okay, so for node 4, you're saying
It is 14 10 9. I don't know if I run
okay,
one more cycle whether it is 8 or it's 9.
okay, there is 4, 4, 2. Okay, so you're saying shouldn't I check for one more time to see that it actually stabilizes, right?
Yes.
That is your question.
Yeah.
Yeah. So it is guaranteed to stabilize, right? So in a way, we need not check. I think that is the whole point. Of course, you can run it one more time and compare the nth and the n plus 1 time, but is it really required?
No, is it so ki if n minus 1 node gets stabilized, then the last node has to be stabilized? It is some kind of this sort of analogy. Because with
Yeah,
one
yes.
node I cannot make any cycle. Is it something like that?
Uh, let me just. Oops. Step. Yeah. Sorry. So you're saying no. See, because after n minus one time, right? You have, so let's say the initial vertex was 0. Uh, uh, so the first time you go towards paths with 1, second time you go towards paths with 2, then you continue this, and the nth time, if at all there is a path, that path will be from 0, let's say back to 0, because you have traversed n nodes, right? Now, if you try for the n plus 1th time, it is like you are going from 0, you have come back to 0, and then you are going towards the neighbors of 0, whichever that is.
Hmm.
And that will, of course, be greater than the previous step, right?
Greater than previous step means I didn't get that.
Okay.
Means if I run one more time, then instead of 5, I will see this is 6.
No, you won't see that, because we are taking the minimum always,
Yeah.
right? Okay, let me just think about it. So assume that there is a path like this, okay, which goes all the way and comes back to 0. Okay, so it takes, yeah. So this is 1, 2, 3, 4, 5, 6, 7. Yeah, 7 and 8. Okay, so we have run it 8 times, and we realize that there is a path which goes from 0 to 0, right? Now, the next time we run it, we will get a path which goes from 0 to 0, and let's say towards 1. Oops, sorry. Sorry about that. Yeah. The next time we run, for the n plus 1th time, we will get a path which goes from 0 back to 0 plus 1 more time, right?
Hmm.
And this path will have a weight which is greater than this path. Because the condition is there shouldn't be any negative cycles. If there was a negative cycle, definitely it will be lesser.
Yes.
Okay. So that means if after n, whenever you go ahead to the n plus 1 path, you will again be going to a node which you have already visited, and in a way you're adding additional weights. So, and if you look at in our code, so the code, we are always capturing the minimum distance.
Correct.
So it won't capture the n plus 1, the n plus 2th distance.
So it will repeat the value of the minimum.
It will repeat the value. Yes.
I'm just correct.
Yeah,
I'm just have a doubt whether note 4 will repeat or not, because for the note 4 the value is not stable even in the last step. That is my question.
Now it is stable, na? It is n minus one step. So that's what induction says. After n minus one step, the algorithm will stabilize. Now it is stable. Now you can cross check as well.
No. How do you say in this step ki algorithm is stabilized? How do you know that?
That's what sir has proved in the lectures, right? And it is proved by induction.
Acha. I have to take by
let me
induction.
see.
Acha.
No.
No, it is stabilized for all the nodes because the n minus 2th step and the n minus 1th step, the value is same. I can see ki it is converging and stabilized, but only I have a little doubt with the node number 4 because it is still decreasing. That is why I am asking this question.
Okay, how is it still decreasing?
Sir, 14, 10, 9 in this fashion. Node number 4, sir.
Sir, he's saying it is decreasing from n-1, n-2 to n-1 update. From 10 to 9. He says it is still updating.
Oh, okay. So you're saying maybe in the next one also it might reduce. That's what you're
Reduced to
saying.
8. What I am saying, it is not, because if you repeat one more step, then it might be comes at 9. Then I can say yes. Now I am pretty sure ki it is stabilized. This is my question, sir.
Yeah, I understood. Okay, so we are starting from 0. Okay, and we are saying from 0 to 4, the shortest path is 9, right? And let's try to see which is that.
12.
Is it this? 8 plus 1, 9, 9 minus 1, 8, 8 minus 2, 6, 7, 10. Okay, no, it's not that.
9.
Can you identify that part?
Yeah, it is 0 to 7, 7 to 6, 6 to 1.
No, is it
6,
6 to? Sorry, go ahead.
6 to 1, 0 to 7, 7 to 6, 6 to 1, 1 to 5, 5 to 2, 2 to 1, no, 2 to 3, sorry, 2 to 3, then 3 to 4.
2 to 1.
2 to 3, then 3 to 4.
Okay, very nice.
8 and 1, 9, 9 minus 4, it is 5, 5 plus 2, 7, 7 minus 2, 5, 6, 3, 9, yeah.
Okay.
Excuse me, can I come
and
for a minute?
this is, sure.
The issue here is that actually if you see the program, it runs for n times instead of n minus 1. This is just to check that the algorithm has stabilized, because if you go after this step one more, then you will see the same numbers repeating. So you will be going to have 0, 5, 5, 6, 9, 7, 9, 8.
Naveen, how it is running and updating n times?
If you see the outer loop, it runs up to the full rows.
Yeah, just to make sure.
Yeah, so it is not n minus 1 time, it is n times it's running actually. Right. So actually in this, to the best of my understanding, it's not the individual node which you can stabilize, but it keeps on, the numbers keeps on changing as it is happening here in case of 4. And at this point in this table, actually he has, it's shown right now that this is the final one, but actually in the lecture, he actually said that if you go one step further, you will see the same numbers appearing. And if the same number does not appear, that means there is an instability.
Exactly. That is why I am asking ki here if you see ki here 0, 1, 2, 3, 4, 5, 6, 7, 8. So total 8 times it's run because it is 0 to 7.
Yeah.
In this say. So I have to run this algorithm for the 9th time ki see ki every node gets stabilized.
There are 8 vertices.
Yeah, that is why 8 vertices, 8 runs.
So you have to run for the 9th time and then you will see that.
And
that's what is actually happening in the program.
Yes, that is why I am asking. In this table, if one more step is there, then it is pretty clear. Actually, sir, drawn in hand.
He argued about it, that you run another step and you'll get the same numbers. If you don't get it, then there is some negative cycle.
That means in practical purpose, when we are actually testing this, we have to run it 9th time, not 8th time.
It's already running in 9th time.
Yeah.
No, it is 8th time running.
But in the table, it is running 8 time, right? You are right.
Yeah.
But what the point which sir was making is there is no need to run it for the 9th time because you have already examined all paths of length 8, right?
Yeah.
So what does that mean? That means that if if at all there is a path of length 8, that means that that path has traversed all the nodes of the graph, right? And let's assume that there is a path of length 9. Okay. If there is a path of length 9, that means at least one of the nodes are getting repeated, at least, right?
Right. Right.
And that means the distance also gets added. And that means that new, whatever is this ninth row's value, uh, uh, yeah, so that will not, so we will most definitely be adding some things to in the ninth run, and that will only increase this value. And since we are looking at the minimum, so we are sure that it will not be lesser than this, the final what we run in the eighth time. Shamit, not convinced?
Okay, sir. I heard. I will just think in my own time and then again come back, sir.
Sure, sure.
I may need some time.
Come back.
Yeah, definitely.
Yeah.
Definitely. Others, any other thoughts? It's only few of you who are interacting. Can anyone give a better argument about why in the ninth time it will always be equal to this?
Sir, honestly, I'm lost. I'm just trying to pick up bits and pieces from in between, honestly.
First column in this table, it is the initialization step. So after that, the code has run 7 times. If you run it once again, then if the value decreases from 9 to the value of 4, the value in last column of 4, if decreases from 9 to something else, then there is a negative cycle. This column, this first column is just initialized. When we assign the 0, we assign the distance of 0 to itself, just for the purpose of
Okay.
just to give a push to the algorithm.
Right.
Sir, this table is updated only n-1 time. That is 7 times only. But the code, whatever sir write in the slides, is running n times.
So you're saying there should be one more cycle, one more entry here, right? Yeah. I'm saying even if that is there, yeah, let's say if it's there and if it stabilizes, right? So you're saying this is the first time, second, third, fourth, fifth, sixth, seventh, eighth, whatever it is. Let's say that was missing. We add that, and let's say this 9 became 8, for example. Okay. But then we can be sure that once it runs for 8 times or n times, we can be sure that in the ninth time it will be equal to this. That's all that I'm saying. Because of the argument that in the ninth time we will, if at all there is a path, that path will cross 8 vertices, and it will result in the nodes getting repeated. And since at least one node gets repeated, the weight also gets added, which will result in we will get a higher weight. So
But
in
sir,
that case,
this will never get updated in eighth update, because that's what sir said now. N minus like Benwell Ford stabilizes it maximum n-1 iterations.
exactly, it will stabilize. I'm saying you will not get a value because you will always keep on adding. And because of that addition, if you notice here, we are always calculating the minimum. right? So distance of V will be, in this case, for example, let's say it is 8. Distance of V will be 8, and distance of U plus whatever is the new weight. So let's say 8, and this becomes 8 plus 10. So this plus whatever is the new edge from U to V, that will have a weight, and that will always be greater than this distance. And since we are calculating the minimum, this will always be the minimum. The current distance will always be the minimum distance. So we can be sure that it is stabilized. Okay, so I just wanted to check how do you all, I want to hear from the others also. How do you all try to understand this algorithm? Do you uh, check line by line? Do you make some drawings? Do you create tables? What do you do? I want to hear from the others also. We'll take a slight pause. Yeah, by then you can tell me. Drawings, tables,
Sir, I also
usually make.
tables as Madhvan sir used.
Okay. So are you able to understand from that?
Yes, sir.
Do you all use visualizations which are there on the web? Do you check it out? Okay, I had some good visualizations which.
Is there any site, sir, to check the visualization?
Yeah, I'm just sharing some with you all. So you can just search online. I also just searched online and I uh, got these. Okay, this is Dijkstra and Floyd Warshall. Okay, so let's move on to prims and Kruskal's, right? Yeah, Neeraj, Python tutor is also a good resource. Okay, why don't we do one thing? We'll just take a quick 2-minute break. Why don't you all just visualize? I've sent 2 links. Why don't you just go through it and uh, just pick any one algorithm? Okay, let's pick Dijkstra's. Hmm? And let's see if how we can go about doing that. We'll just take a quick 2-minute break. Huh? Okay, any thoughts on the visualizations? Is it making it easier to understand or more difficult or getting some idea? Any thoughts? Yeah, one thing is that you need to get some idea about the algorithm, before you actually start doing the visualization, or you will get lost. You need not know everything about it, but at least if you know some things about it, then it definitely helps, right? And there are a lot of like YouTube videos or other things also. Since those resources are available, you should check it out to get a better understanding. All right. Okay, so I think we can move on to spanning trees. Some of you had doubts regarding the prims and the Kruskal's algorithms. Any specific doubts in that? All right. Hmm. So let's try the animation also. Okay? I mean the visualization also. So, okay, can any of you tell me what is a spanning tree? Anyone? Or what is the minimum cost spanning tree?
So spanning tree is like a path that will cover all the vertices in the graph. And if the weight of all, like some of the weight of all these paths is minimum, then we will call it minimum spanning tree.
Right, very nice, very good. So it is a
Spanning tree,
minimum. Yeah, go
spanning
ahead.
tree is a connected graph with uh, minimum number of edges.
Very good. Right. So it is a connected graph with the minimum number of edges, right? And by minimum, can you specifically tell it has exactly these number of edges?
A tree will have n minus 1 edges.
Exactly. It will have exactly n minus 1 edges. Why? So let's say if there are like 3 edges, or let's say there are 4 edges, and it's like fully connected like this. So the spanning tree should connect all the edges, right? And since there are 1, 2, 3, 4 edges, the spanning tree, sorry, 4 nodes, it should have, let's say, 1, 2, 3, 4 edges. If I try to add one more edge, then a cycle is formed and it's not a tree, right? Okay, Abhijit is asking, there isn't any notion of a parent node and child node in a graph. Yeah, in a graph, we usually don't, we usually don't call anything a parent or a child. It's mostly in trees. Right?
So in directed graph, there can be parent and child graph, child node, parent and child nodes.
Yeah, of course there can be, but usually the terminology which we use, parent and child and all of that, is usually for trees. Even in directed graph, no, I'll tell you. For example, if we have something like 1 to 2, then 2 to 3, say 3 to 1. Now, which is a parent of which, right?
Yes, in cycles, it will be difficult.
Yeah, in cycles it's a little difficult, right? So that's why usually for trees only we refer to parent and child. Okay. So prims and cruscals, the main idea is to calculate this minimum cost spanning tree. So what we do in prims, right, is to start with an empty set of so this is the this is the thing which we are interested in, right? NBR, or which is which we initially initialize to an empty dictionary, right? What we do is we start everything is initialized. So visited is false. Visited for all vertices is false. Distance for all vertices is infinity, right? And NBR is for all is -1, right? Now what we do is we start with any vertex, right? Let's start from, let's say, 0, and we set visited of 0 to true, right? Then we look at the neighbors, okay, of 2 of 0, right? In this case it is 2 and 1, right? And we initialize the distance so v comma d, which is v in this case, this is v, let's say this is v first. Distance of v is equal to d, which is this 80, right? And NBR, or the neighbor of v, is 0, right? And the same thing we do for this 0 to 1. We initialize this, we keep this as v, and this is 10, right? Now the actual algorithm starts, where we actually try to identify the next vertex which we need to add to our tree, right? So what we do is we look at all the vertices which we have not visited, right? Okay, so let me try to maintain. So visited is there, 0, 1, 2, 3, 4, 5, 6, right? So from 0, we see which all are not visited, and we take the minimum, the one which has the minimum distance, right? So we have two options, 80 and 10. We choose the one with the minimum distance, so we choose 1, right? And that is the next t is nothing but the next distance, and next v list, right? So there can be neighbors which have the same distance, right? So let's say there was something else like 7, which also had distance 10, right? So whichever is not visited and has the same distance, we choose that, right? And we take the minimum of that, right? All right. So now we connect 0 to 1, right? Yeah, and we set, so next v now in this case becomes 1, right? Next v is equal to 1. And a visited of next v. So this visited also becomes, so 0 is true, 1 is true, right? And now we look at all the neighbors of 1, right? And if it is not visited, we update its distances, right? By looking at which is the minimum distance, and we set the neighbor of that as next v, which is 1. Right? So we continue this process until we get, so now again next 1, right? We look at all the neighbors of 1 which are not visited. So it can be 6 and 20. 0 is already visited. So then we connect this. Now we look at 2. We look at all the neighbors of, sorry. Now we look at the edges whose distance is 0, right? And which are not visited yet, right? So, and we take the minimum of that, right? Is that we look at the minimum of that. So the next vertex, which is not visited, right? So, and then the minimum of that is, so there is 70, there is there is 20, right? So we continue this until we visit all the, we continue this, right, n times, because, at each step we are adding one edge, and after n times we get the entire tree, right? So let's look at how this is getting visualized, right? So here the terminology is a little different, right? It is known as nothing but visited, cost, and they have something called as the path, right? So let's see. Okay. Oh, you need the start vertex. So let's say we start from 0. So initially, let's look at the, okay, I don't know if we can see the code and this. Oh, okay. So initially, what are we doing? We are setting everything to infinity and visited of 0, right? A distance of, distance or cost is 0, and visited of 0 is 2. Okay, if I step forward, right? Known or visited is true, right? Then what we do is we look at all of its neighbors over here, right? So which are the neighbors of 0? There's only one, which is 4. So in the next step, it will look at 4, right? And it will see how much, then it will look at the minimum of distance of V. So distance of V in this case is infinity and D, right? In this case, D is, what is the value of D? D is 8. So since infinity is greater than 8, so it will take the minimum, right, and update it to 8. And the parent or the neighbor, path in this case, or the neighbor is 0, right? So this gets added to the tree. Then we continue this next time. Oh, sorry. Right, vertex 0 is known. Yeah. Now in the next step, we look at which is the minimum in this distances, and as well as, which is not visited, right? So, and that is 4, and 4 is set to true. And then we look at, we need to calculate, so next of D in this case is 4, right? And we look at all the neighbors of 4, right? In this case, 4's neighbor is only 1, which is 6. 0 is also a neighbor, of course, but 0 is already visited. And then we look at 6, right? And we look at the distance, and we compare the distance. We see that infinity is greater than 8, so we replace it with 8. Sorry, we replace it with 6, right? The minimum of that, which is 6. And the parent becomes 4, or the neighbor becomes 4, right? Then again, we look at the minimum of the cost, right? It is 6. So now our next D, or the next node becomes 6. Now we look at all the neighbors of 6. In this case, we have 5, 1, and 2, right? So 5, 1, and 2. Now we set it to true and look at its neighbors, right? Right, for each of them, it is not visited. So we update that. Then 1, 2 also we update. 4 is already there. We look at 5. We update 5. All right. Then this process continues. So at each step, we are updating, adding one node to the spanning tree. And we continue this till we reach the, till we iterate n times. And at each, so then we will get the spanning tree for the entire. So I'll just play this. So now it's looking at 2. Yeah, but this is very fast. So yeah, so you all are getting an idea of what is happening, right, in the spanning tree for prims. Any doubt in this algorithm? So this is one way you can do it. Like, try to understand the code, try to look at the code and this visualization, try to see what is happening, and that can give you a better idea of what's happening. Any doubts or completely blanked out or difficult? Okay. So then in Kruskal is building it. This algorithm, it is building up in a bottom-up fashion. Okay, so let's try to look at what's happening here. Okay, so in Kruskal, what is happening is, what we try to do is try to create, so what we do is we try to, let's say 0, 1, 2, 3, 4, 5, 6. Each of them, we consider it as a component. Okay, so we have edges which are initially empty, we have components which are initially empty, and TE is nothing but the tree edges, right? So what we do is we put all, we extend or we add things to our edges list, right? Which is nothing but a tuple which contains the distance at the start, right? So distance is nothing but these weights, right? And U is the one part of the edge, V is the other part of the edge. For each V comma D in the list, in the adjacency list or matrix for you, right? So for each neighbor, so we take each of these keys. So we take 0, we look at its neighbors, and we add them to the list based on the distance, right? And then what we do is we do edges dot sort. We sort the edges. Okay. So can anyone tell me what will the edges list look like now? What is the first element in edges for this example? Okay, Shiva is telling 4, 6. Do you all agree with that? Or is it something else? Okay, so yes, it's 4, 6, but remember we are adding D also, right? So the distance is 5, 4, 6. Oops. Okay. Next entry. Okay, can someone help me? Just unmute and speak. Yeah. Next is 6, 1, 2. Then
Then comes like the 3 here again, 10, 0, 1, and then 10, 5, 6.
okay.
And after that we have 20, 1, 4.
We have 20, 1, 4. Okay.
Then 50, 4, 5.
Okay.
Then 70, 2, 3.
Okay.
And 80, 0, 2.
All right. Others confirm that this is correct, the entire thing. All right. So we have this edges list. Okay. Now what we do is we take each of this, right? Oh yeah, another thing. Component is another data structure which we have. Component, initially, component of a particular vertex is the vertex name itself, right? So what we are trying to do is, the broad idea is each of these vertexes are components, and we try to combine them together until we reach, so in this case, initially you can see all of them are separate components. We try to combine different components together till finally the output should be, we should get one component which will have all the vertices connected to each other. And that is nothing but the spanning. Okay, so that is the broad idea of Kruskal. Okay, so let's take, in this case, we have, yeah, then we iterate through the edges, right? And we look at whether the starting of the edge, the component of that and the component of the other side of the edge, are they different? Okay, we'll come to why that is the case, but let's assume that. Okay, so let's start with the first one. So first one is, what is component of 4? Can anyone tell me initially what is component of 4? No answers? Okay, some of you are saying 4. Right, look at this. Initially, we have initialized component of u as u. Component of 0 is 0, 1 is 1, 2 is 2, 3 is 3, 4 is 4, 5 is 5, 6 is 6. Oh, you have only till 6. Okay, right? Okay. Now what I'm checking is, now I'm here. Now u is 4, and okay, let me write it in. U is 4 and b is 6. Now, is this if condition true or false? Component of u, which is component of 4 is 4, component of 6 is 6. Both are different. So what that means is both are still not in the same group. Both are not connected yet. Okay. So that means I can connect them now. Okay. So TE, which is my tree edge, okay, I will append TE is a list. I will append 4, 6, which is my u, v into that, and C is the component of u, right? So C, in this case, now it will be equal to 4, right? So what I'm doing is, yeah, I'm connecting 4 to 6 and the edge weight is 5, right? Now what I do is I look at all the other nodes, right? And sorry, I look at all the now what has happened is the component, yeah, now initially the force component was 4. I'm just mentioning it here, and 6's component was 6. But now we have combined them together. So now this actually forms a new component. Okay. So this forms a new component and we have to give it a name. So it can either be 4 or 6. So in this case, what we have done is whatever is the bth value, right, that becomes the component. So we have initially stored C as 4. We iterate through the keys, and whenever we encounter 4, right, whenever we encounter 4, we are saying, okay, now don't, it was initially 4, don't do, make it the component of V. Component of V is 6. So now 4 and 6 form a new component, right, whose name is 6, right? We continue this. Okay, so this is done. We continue this for all the edges in the edge list. Next is 6, right? The distance is 6 between 1 and 2, right? So now my U becomes 1 and my V becomes 2. And yeah, and I up and okay, so now let's look at the component of U. Okay, that is still 1. Component of V, which is 2, is still 2. Both are different. Right, great. So we can combine them. And we add it to the tree edge, which is comma 2. And now C is actually the component of 1, which is 1. And now this was 1 and 2. Now component of 1 changes to 2. Now this forms another component, right? And this is another component. So we have 1, 2, and now we have 3 more components, right? We continue this, right? Now we look at the next edge with the minimum weight, which is 10 and 0 and 1. Okay. Now we look at 0 and 1. What is the component number of 1? Can anyone tell me? What is the component number of 1? Component number of 1, Sri Krishna is telling 2, right? The previous step, it was initially 1, but then now we changed it to 2. It is part of this component, right? This is component number 2, component number 6. Yeah. And we see both are different, right? So since both are different, we can combine them, right? So I add this tree edge 0, 1, and now 0 also becomes part of 2, right? So I do this, then I go 5 to 6, right? 5's component is 5, 6's component is 6. Both are different. I add it to my tree edge, which is 5, 6, and it becomes 5 also gets captured in this, right? Okay. All right. Now I go to the next minimum one, which is 20. 1, let me see, 1 is in the second component, 4 is in the sixth component. Both are different. I join them. And now this entire thing, right, will be part of, like, the convention which we have used is 1 to 4, whichever is the vth thing, we'll give it that. So this entire thing now becomes 6, right? This entire component becomes 6. All right. Yeah. Now, yeah. So now we go to the next one, right? 4, 5. Now you see that 4 and 5 both are in the same component. Okay, now you'll understand why both have to be different. Okay, why are we checking for that? We are checking for that because let's say we don't have this check, right? If we don't have this check, what we'll do is we'll connect this. So we'll connect U and V, which are of the same component. And so what does that mean? Since U and V are in the same component, they were connected somehow, already, right? So in this case, you can see 4 and 5 are already connected via 6. But if we don't check if they are in different components, what will happen is we'll end up connecting them and we'll form a cycle, right? And that's the reason why we have to always see that both are in different components, right? So in this case, we won't do anything because 4 and 5 are in the same component. We'll just skip it. We'll go to 2, 3. Yes, 2 is in the 6th component. 3 has not been connected anywhere, so it's still in the 3rd component. And we connect that, right? And so now 3 also gets added to this big component called 6. We add it to the edge, which is 2, 3. Now, yeah, 0, 2 is also in this, both are in the same component. So I hope we have got it. Yeah. So finally, this is how it is, right? Um, let's see if we have got it right. So the three edges are 4 is connected to 6. Okay, let me follow the um, oops. Okay, 4 is connected to 6. 1 is connected to 2. 0 is connected to 1. 5 is connected to 6. 2 is connected to. Hey, did we miss something? 1 to 4 also. So we get this value. Right? Notice how this is different from prims, where in prims we are, starting from a particular vertex, and from that we are looking at the ones which have the minimum weight, right? And we are slowly increasing the tree from that particular edge. Whereas in Kruskal, we have all the edges and we are looking at the minimum one, and we are combining different components together to get the big tree. Any doubts in this? Got an idea of how Kruskal works? I think there is a visualization for Kruskal also. Let's see. Okay, let's see how this goes. So in yeah. So here you can see that you can have an adjacency list also. Oh, yeah. So yeah. So what it's saying is that we look at the one with the minimum distance, right? So we have 0 to 3 with 1, 1 to 5. Okay, let me take a better graph. This looks good. right? So okay, so what it has done is, okay, it hasn't sorted the edges yet. Let's see what happens. Yeah, now this is that edge dot sort. Remember this part. It's sorted everything, and it takes the first. Okay, then now what do we do after we do the sort? We check if both are in the same component, right? So this refers to the components, right? I think, right? It is checking for 0, and it is checking for 2. So vertices are in different trees. So add edge to tree. Okay, let's see what it's doing. Okay, so it's a little different, the representation. So don't get confused by that. Then what it did is looked at 2 and 5. 2 is in, okay, I don't know why they wrote this as -2, and 5 is in -1. So I think yeah, they are in different edges, so they're in different components. Vertices are in different trees. Add edge. So it adds that. Yeah. So yeah, so I don't want you to get confused by this. Yeah. So that's the main difference between Prince and Kruskal. Okay. So any doubt in this? Okay, I hope you understood. So now what is okay? Now what can anyone tell me what is the complexity of Kruskal's algorithm? Anyone wants to try? Okay, I'll ask a simpler question for okay, what is the complexity for this for loop? Let's start with each. Complexity of this for loop. N into M. So remember, yeah, you're running this N times. And we are looking at the adjacency list, right? Yeah, because there is another loop inside, right? Right, Snehal. So remember, look at this, there is another loop here, and that is going through the
So why not
neighbor.
m plus n?
Yeah, Shruti, but sorry, I didn't hear you.
Sir, why not m plus n?
M plus N. Okay, why do you think so? M plus N?
Because it depends on how long the adjacency list is, and we can safely say that if the number of edges is only n minus 1, then it seems to me like once you have to go through all the rows, and then you just have to go through the total number of edges, right?
Yes, yes. Okay. So what? Okay. So let's say we are going through each of the nodes, right? And each time we are looking at its neighbors, right? And at most there can be Yeah, so I would say that this whole thing will take order M. Do you all agree or disagree?
Yes, sir.
So what we are doing is we are just looking at each time we are just looking at its neighbors, right? Neighbors of the first node, neighbors of the second, neighbors of the third. How many of them there are? At most there will be 2m, which is order of m, right? Okay, got it. Now this one, how much do you think this will take?
N log n.
Right. We know the best algorithm like a merge sort or something will take n log n. Great. So this much is n log n, right?
Yes, sir.
Okay. What about this?
So the outer for loop is m again.
Hmm. So we are running this n times.
And yeah, I got it. So the inner for loop will have. Actually, I thought that the graph is minimally connected, but then I realized you can have more than one edges.
Right.
So yeah, m and the second loop will be n, so it will become m into n.
Right. So this will be m into n, right? Right. Okay. Good, good. Yeah. So now what yeah, and whereas if you see in prims, yeah, let's look at prims. Prims, can you tell me? Prims, we can see that there is, okay, this is going through the nodes. So this is like n, and inside n, we can again see that there is again one. So for each node, we have to calculate its minimum distance, right?
Yes.
Yeah. So what we learn in week 6 is that is there a way to come up with better data structures which will help us actually calculate the minimum without going through the entire dictionary. Okay, so so if you see this step itself, right, it's going through the entire list and looking for the one with the minimum distance. This itself is taking n. So the order of this is becoming n square directly just by this step, right? And I think the same, yeah, right? So so in week 6, what we will see or what we all have seen is that there is a data structure known as a heap, which will help you get the minimum or the maximum, the minimum, okay, in less than order of n time, right? So yeah, so that is a quick teaser to what is there in week 6, right? Okay, I hope you all have understood Prims and Kruskal. Any doubts? So I think that was the question, right? Minimum spanning tree, how do you develop it? Any doubts in Prims and Crucible? I think that was a doubt which many had. And someone asked me about this trees. I forgot who it was. Can you elaborate? I'm not sure what your doubt was. Okay, I won't go through the code now, but yeah. So I think how do you represent such a structure, right? So one way to think of this is as a linked list, right? Which has node value, right? And which has a left and a right, right? So since this is a tree, and this is known as a binary tree, where each node has a left and a right child. So now left will point towards another node, right? So in this case, if you see, which has value 37 and a left and a right node, that will point to, let's say, 16, right? And 44, right? So this is how a binary tree can be represented, right? And this is, I guess, one efficient way to represent that, because how else will you represent it? You cannot represent it in a list or an adjacency list. Is it possible? Maybe. So for example, you have 52 and you have, say, 37 and 74. But what is missing in this case? Can anyone tell me? So I can have something like this, right?
Yes, sir.
What is the difference between this and this?
Sir, I didn't understand the question. What is the difference between?
So this is one type of representation, the one on the top, this one, right?
Right.
And I'm saying this is another possible representation where you have this as an adjacency list.
Yes, but in this case, will it be a little tough to compare it with all the other predecessors? And to keep count of which one was on the left and which one was on the right?
Exactly, right? So for example, if you take 16, right, you have a value called 28. Now, is 28 the left child? Is 28 the right child? That information is missing here, right? So that's the reason why this is an appropriate data structure to represent binary trees. And this makes traversing it also easier, right? So let's say we wanted to go from 52 all the way down to 16. You know this is the path which you should take. Whereas in this case, it's not evident, from 50. Can I reach 50? Can I reach 16 from 52? Well, I have to look at all the paths from 37. Then I have to look at all the paths from 74. So it's not entirely clear, right? How to do that. So that's the reason why such a representation is appropriate, right? So I think that was the doubt which, yeah. So the question was, why should we use a linked list? Why not something else? So this is an explanation of that. Okay, we are running out of time. Anything? Okay, that's, I think we can stop now if there aren't any other questions. Okay, everyone. Yeah, so please go through week 6 also. It builds upon what you learned in week 5, but you will be looking at data structures like heaps, which will heaps, and you have the union set. Yeah, so that will help you. Those data structures will for the algorithms which you learned in week 5. Okay, everyone. See you then. Take care. Bye. Good night.
Okay, sir. Thank you, sir.
Okay. Bye.
Thank you, sir.